Late 1940, Princeton University. A graduate seminar, physics department setting. Richard Feynman arrived there, doctoral research in progress. 22 years old, early academic stage, working alongside John Archibald Wheeler, developing a radiation theory. Later identified as Wheeler-Feynman absorber theory, the proposal was unconventional, time-symmetric electrodynamics, retarded wave solutions, advanced wave solutions, forward temporal influence, mathematical backwards symmetry, permitted by equations, debated in interpretation. The seminar gathered several senior physicists, organized with involvement from Eugene Wigner. Present in the room, Albert Einstein, Wolfgang Pauli, John von Neumann. All internationally established, all intellectually dominant. Feynman was not yet. Before the seminar began, Einstein entered quietly. He greeted Feynman, simple acknowledgement, then asked directly, "Where is the tea?" A small recorded detail, later written in, "Surely you're joking, Mr. Feynman." The seminar opened. Equations covered the blackboard surface, derivations unfolded carefully, step-by-step argumentation, the framework removed fields, replacing them with interaction, particles influencing directly through universal absorber response, ambitious in scope, precise in formulation. The presentation concluded, discussion immediately followed. Wolfgang Pauli responded first. Wolfgang Pauli raised structured ejections, technical consistency questions, implications examined, limits clearly identified. No theatrical exchange recorded, only concentrated critique. After outlining concerns, Pauli turned toward Einstein, a procedural gesture, common in academic seminars. He asked whether Einstein agreed. The room paused. Senior authority present, expectation naturally shifted. Einstein answered calmly, no endorsement offered, no categorical dismissal issued. One concern identified, gravitational correspondence. He noted difficulty extending the framework to gravitation. That was the extent of his formal response. No sweeping verdict, no generalized rejection. One domain specified, nothing beyond it. Discussion subsided, no resolution declared, no final ruling imposed. The absorber theory remained open. Historically, it later proved incomplete within quantum mechanics. That outcome developed in subsequent years, but Princeton 1940 remained instructive in structure. A young researcher presented, senior physicists evaluated. Criticism was applied, authority responded narrowly. Decades later, Feynman described Einstein as very tolerant of ideas. Tolerance meant restraint, measured intellectual boundary, commenting only where deeply grounded expertise existed. The seminar ended. No announcement followed, no institutional declaration made. Just a documented exchange in late 1940 at Princeton University. That is the event. Princeton's atmosphere, intellectually intense. Reputations were immense, standards even higher. Richard Feynman stood there, young but precise. Equations defended carefully, logic aligned stepwise. No rhetorical flourishes, no dramatic tone. Only structured reasoning, mathematical clarity. The objections mattered. Wolfgang Pauli was exacting, rarely casual in criticism. If inconsistency appeared, he would expose it. If ambiguity surfaced, he would isolate it. This was normal procedure, not personal hostility. Scientific culture demanded rigorous internal coherence. Feynman responded directly, clarifying assumptions. Time symmetry defended, causality interpreted differently. Advanced solutions allowed, but globally constrained. A universe-wide absorber. Future boundary conditions included. Uncomfortable idea, yet mathematically permitted. Attention then shifted toward senior authority. Albert Einstein remained composed, observing without interruption. His reputation unmatched, architect of relativity. Any statement from him carried disproportionate weight. He did not dominate. He selected one issue: gravitational consistency. If interaction replaced fields, what of spacetime curvature? How would gravitation fit within that framework? The question was focused, not expansive condemnation. He did not declare, "This is impossible." He did not state, "This is wrong." He identified a boundary, then stopped there. This restraint mattered. In later reflection, Feynman emphasized Einstein's intellectual discipline. Not omniscience performed, not authority exaggerated. Knowledge confined carefully to its domain. Outside that domain, silence preferred. That silence carried meaning. It demonstrated something rare, especially among experts: comfort with uncertainty. The seminar culture rewarded precision, not theatrical certainty. Questions were sharp, answers equally sharp. But limits acknowledged when limits appeared. Feynman absorbed that lesson. Years later, in his own lectures, that attitude resurfaced. Admit what is known, separate what is assumed. Do not oversell conclusions, do not conceal ignorance. This pattern became central to his scientific persona. Not performance science, but accountable explanation. Even when wrong, be transparently wrong. The absorber theory did not become foundational. Quantum electrodynamics evolved along different paths, eventually culminating in renormalized field theory. Names later associated Julian Schwinger, Shinichiro Tominaga, and Feynman himself. But 1940 remained a formative environment. Exposure to criticism without intellectual collapse. Exposure to authority without intellectual intimidation. A room of giants, yet structured dialogue. No applause recorded, no humiliation either. Just physics discussed within defined boundaries. The deeper principle emerged quietly. Say exactly what you mean. No more, no less. If evidence supports it, state it clearly. If extension is uncertain, mark it uncertain. If knowledge ends, stop there. That was visible in Einstein's response, and unforgettable. Years later, 1951. Brazilian education project. Richard Feynman traveled there, observing institutional structures. The goal was instruction, teacher training initiatives. Science education development, government collaboration. Not seminar debate, not theoretical controversy. Classrooms and pedagogy, systemic learning processes. He encountered patterns. Students memorized answers without conceptual ownership. Teachers delivered content without encouraging questioning. Correctness measured by repetition, not understanding. This mirrored larger systems. Authority validation structures incentivizing compliance. Students seeking approval before trusting reasoning. The psychological mechanism. Ideas feel legitimate only after external endorsement. Grades function as signals. Performance metrics replace curiosity. Approval becomes prerequisite for intellectual confidence. Feynman criticized this directly. Not with emotional rhetoric, but practical observation. Education should cultivate understanding, not mechanical obedience. Questions must be encouraged, not suppressed. Errors are informative, not moral failures. Knowledge grows through exploration, not rote certification. These remarks caused debate. Institutions defend established methods. Teachers value structure, standardized evaluation. Governments seek measurable outcomes. Innovation challenges existing systems. Tension is inevitable. But the core issue remained. Learning as independent thinking versus learning as compliance. Feynman argued for the former. Students capable of reasoning require fewer external validations. They evaluate evidence directly. They adjust beliefs logically. They do not require permission to understand ideas. This principle parallels Princeton. The seminar demonstrated intellectual boundaries. Critique applied precisely. Authority responded narrowly. No generalized dismissal. No exaggerated endorsement. Knowledge advanced through discussion, not hierarchical decree. Brazilian experience reinforced it. Systems can unintentionally discourage curiosity. Standardization has value, but limits must be recognized. Education should enable thinking, not merely certification. Feynman's position was practical. Science depends on questioning. If questioning disappears, progress stagnates. Authority becomes substitute for evidence and reasoning. This is intellectual risk. Institutions must balance structure with independent exploration. Rules exist for coordination, not suppression of ideas. Understanding requires engagement. Memorization is insufficient. The Brazil project ended, but lessons remained. Feynman later referenced these themes in lectures and writings. Clarity of thought, honesty about uncertainty, willingness to examine assumptions. These qualities define science. Not deference to status, not blind acceptance. Evidence and reasoning, that is the standard. Historical events inform understanding. Method matters as much as outcome in science. Knowledge advances through discipline. Arguments succeed with evidence. Status does not guarantee correctness. Ideas require evaluation. This principle applies broadly. Economics, technology, governance. Education systems shape reasoning. Structure can enable learning, or unintentionally discourage curiosity. Standardized assessment measures performance. Useful for coordination, but memorization alone insufficient. Understanding requires engagement. Questions should be welcomed. Exploration builds competence. Feynman's reflections in Brazil reinforced these observations. Teachers sometimes emphasize compliance. Students reproduce information without internal comprehension. Learning becomes mechanical, not intellectual growth. Systems value measurable results. Efficiency has advantages, but independent thinking matters. Societies require adaptable minds. Citizens evaluate information critically. Democratic participation depends on informed judgment. Technology amplifies information flow. Noise competes with analysis. Disciplined reasoning remains essential. The Princeton seminar illustrates professional intellectual conduct. Critique applied precisely. Authority responded narrowly. No general verdict issued. Dialogue remained technical. This structure preserved space for continued inquiry. Even imperfect theories contribute to understanding when examined. Errors guide improvement. Knowledge evolves. Scientific progress is iterative. Ideas refine over time. The absorber theory did not become foundational. Quantum mechanics developed differently. But questions raised mattered. They influenced later thought. Indirect contributions are real. Science builds on collective effort. No single individual possesses complete insight. Recognition should avoid exaggeration. Historical accuracy matters. Hero worship distorts understanding. Achievements emerge from collaboration. Disciplines intersect and evolve. Philosophy informs methodology. Mathematics enables precision. Experiment validates hypotheses. Each component supports progress. This model extends beyond science. Business innovation challenges assumptions. Legal systems interpret principles. Cultural institutions adapt. Change and stability coexist. Rules provide structure. Flexibility enables growth. Balance remains necessary. Public discourse benefits from respectful engagement. Ideas can be debated without hostility. Disagreement need not escalate. Civil dialogue improves outcomes. Modern communication often diverges. Social media rewards immediacy. Complexity is simplified. Opposing views become identities. Dialogue deteriorates. Understanding suffers. Restoration requires effort. Individuals prioritize substance. Communities encourage analysis. Education supports critical thinking. Teachers guide inquiry. Students explore concepts. Learning becomes meaningful. The Princeton example demonstrates intellectual humility. Knowledge has limits. Uncertainty is normal. Acknowledging boundaries enables growth. Pretending certainty invites error. Scientific methodology structures inquiry. Hypotheses generate predictions. Evidence tests claims. Results inform revision. This process reduces bias. It does not eliminate uncertainty, but it advances understanding. Other domains can adopt similar discipline. Policy benefits from data. Business from analysis. Personal decisions from reflection. Reasoning strengthens judgment. Authority remains important. Expertise guides decisions. However, authority should not replace evaluation. Questions remain valid. Verification protects integrity. These principles are practical. They improve outcomes. Historical narratives should inform, not oversimplify. Events at Princeton and Brazil demonstrate enduring lessons. Intellectual discipline matters. Evidence supports conclusions. Openness enables learning. Progress depends on effort. The absorber theory's limitations illustrate scientific realism. Ideas evolve. Initial proposals change. Failure is informative. Learning emerges from revision. Knowledge accumulates. Each step contributes. This perspective encourages resilience. Innovation requires experimentation. Not every attempt succeeds. Value lies in process. The broader significance extends beyond physics. Human understanding is incomplete, but expandable. Dialogue facilitates growth. Critique improves ideas. Confidence need not require certainty. These principles remain relevant. Modern challenges demand reasoning. Complex problems require analysis. Intellectual discipline supports solutions. This concludes revised Part 4, in structured professional style. If further refinement desired, additional iterations possible.